Welcome to lecture number 13 of the course Introduction to Data Science. Today is the first lecture that we will talk about process mining, a topic that is very close to my heart. This lecture will be devoted to process mining where we look at unsupervised problems. In the next lecture we will focus on supervised learning problems in the context of process mining. So the menu for today is to first start by giving a very broad overview of what process mining is. Process mining starts from event data, as we have seen also in the previous lecture. Next we focus on the topic of process discovery. So without having any knowledge of the underlying processes, we try to automatically learn process models. And we will show that there are, let's say, two basic approaches, although there are many different techniques to do so. One is to use a bottom-up approach. If you think of this in terms of a Petri net, this boils down to learning places, or a top-down approach, where it is basically about finding structures using a recursive approach. We will also tell a bit about tooling and applications, but this is not in the centerfold. You can read about this in the book that is indicated here. The chapters that are, let's say, most important are mentioned here. You don't strictly need this. I think the slides will be self-explanatory, but you can use this to dive deeper, or you can use this, for example, if your knowledge about process modeling, things like Petri nets, is a bit rusty. I would highly recommend to read respective patterns in this book. You can also take part in the Coursera process mining course. This is a course that has been taken by over 130,000 people. There you can also, let's say, look into more detail if you want. Okay, let's start by positioning process mining. So process mining is the linking pin between process science and data science. So this course is focusing on data science. That is why, let's say, process mining just has 2 lectures, where we try, in the entire course, we try to cover the entire spectrum. Of course, there are other courses also given here at RWTH that are covering different parts of process science, ranging from automation to operations research and these types of things. Process mining is the linking bridge because it looks at event data, it tries to automatically learn things, and at the same time it is aimed at improving processes, which is very different than most of the, let's say, mainstream data science techniques. So the raw material, the input for process mining is event data, and you can think of event data as rows in a database or rows in a spreadsheet, as you see here. So in this example, every row corresponds to an event that is related to the handling of orders. We may know many things about an event, for example, which person did it, what was the price, what was the location, and all things like that. But the essential information that we need in order to do process mining, we need to have a case identifier, what is the event about. We need to have an activity name that tells us what has happened, and of course we need to have a timestamp. We may have all kinds of other information, like not just the timestamp of the events, but we can actually distinguish between the start event and the end event, and then every row in this table corresponds to 2 events. We may know the resource, we may know information about products, locations, costs, risks, all kinds of things. But the minimal information is that we have a case, an activity, and a timestamp. If we focus on, let's say, the events of a single order, and we zoom into the case column, the activity column, and the start time column, note that there may be many other columns that we are now ignoring. Then if we focus on a single case and we look at the sequence of activities executed for that case, and we can sort them based on the timestamp that we have, then we can follow these sequences that you see here at the bottom. And so this is what we often call a trace, which corresponds to the execution of a case, and it is describing in which order the activities have been executed from the beginning of a case until the end. If we look at the data set, this is still a relatively small data set. We have over 12,000 cases. In this example, these correspond to orders. They generate 80,000 events if we just look at the complete events. So we basically ignore the start events. And if we do that, then we can summarize the data in this particular data set, only focusing at the control flow in this way. So we see all the different process variants called traces, and we can also see the frequency of them. Based on such information, so we take raw event data, just using the information case identifier, activity name, and timestamp, and we can automatically construct process models which explain the behavior that we have seen in the log. And this shows, let's say, that it is quite fascinating that from this raw data you can learn actually very sophisticated and interesting models. So what this process model shows, that was discovered using the so-called ILP miner, it discovers that every case starts with the activity place order. And if you look at our input data, then we see that, okay, each of the, let's say, over 12,000 cases indeed starts with place order. Then after place order, we see that in some cases we start with payment, but in most cases we start with send invoice. So what this process model expresses is that after place order we have two potentially, let's say, concurrent activities, so that they may happen in any order. We are assuming interleaving semantics here. After executing place order, we can execute send invoice, and we can also send pay. In most of the cases we first do send invoice, and only after that we execute the payment. What this PADRWTH then shows is that assuming that the customer paid and we send the invoice, we can execute prepare delivery. So this is a PADRWTH. So this is a so-called AND join. So we need, let's say, the token produced by pay, and we need the token produced by send invoice in order to execute prepare delivery. If we execute prepare delivery, then after this there will be a token here and a token here, and we must execute both make delivery and confirm payment. But again, just like payment and send invoice, that doesn't have to happen in a fixed order. It is also possible that we cancel the order, but we can only cancel the order after sending the invoice and before the payment is made by the customer. So cancel order can only happen if there is a token here and here. So before payment and after sending invoice. Now the most complicated part comes, but you can also see here. So for example, you see this variant which has been executed 420 times. So there are 420 orders where we see the following behavior: place order, send invoice, then a first reminder is sent, then a second reminder is sent, then the customer pays, then we have prepare delivery, confirm payment, make delivery. So what this construct here is modeling allows for behaviors as we see here, because it basically says that we can send multiple reminders after sending an invoice and before the customer made a payment. But in principle, if we execute this activity, a token must be here and a token must be here, but after executing it, the state is basically the same again. So I hope that this illustrates a bit that based on raw event data, it's quite fascinating that you can learn such models. And this is the starting point for, let's say, all kinds of activities that you can do to improve processes. The screenshot that I just showed you was using the open source tool PROM. You will see, let's say, in the course you will use mostly PM4Py, which is a Python-based process mining library. However, there is also, next to these open source initiatives, there is a range of commercial systems. At this point in time, there are over 35, many of them very successful, and they can basically also show the data. What you typically see is that you see slider functionality, and by slider functionality I mean that you can look at the frequent behavior, the highways in your process model that is shown here, but you can also show, let's say, less frequent behavior. So now you see these paths that are sometimes just taken 4 times. So we can look at mainstream behavior, we can see all behavior, including the exceptional paths, and we can also show time. And so here we see the thicker the line gets, and so here thick lines correspond to high frequent paths, here thick lines correspond to parts in the process where a lot of time is being spent. So we can immediately see bottlenecks. What you should remember is that these types of diagrams are based on, let's say, evidence in the data. They're fact-based, so they're not based on some assumptions, and it's also not something like a simulation model. This is what was in the data. This was using Celonis. There are, as I said, over 35 tools able to do these types of things. What you see here is, let's say, exactly the same process, and I'm showing it in a tool called Disco. Disco is from a company called Fluxicon, which was founded by 2 of my PhDs that built a very easy to use tool with your RWTH account, email account. You can also apply for, let's say, an academic license and use the tool. It's very user-friendly. Basically, it can generate the same types of diagrams as you could see in Celonis. So these were the highways. This is showing all the behavior. And here we are looking at, let's say, where the times are being spent. And we can play with this and interact with the data and see all kinds of things. What is important to note is that, of course, this is not a course on process mining, so we will only look at the tip of the iceberg and just see a few techniques. What I've been talking about so far only covers process discovery, only considering the control flow, so the ordering of activities, and this is done in an offline setting. Process mining is much richer, so basically all the process techniques for which there is an offline variant, there is often also an online variant. Next to process discovery, we can do things like conformance checking, building predictive models, etc., etc. This will be covered in the next lecture. Next to the control flow perspective, of course, we can also take a look at time. We already saw that a bit. Data, for example, what are the descriptive variables that are explaining certain choices, certain delays. We can also add the resource perspective, like to add information about what the roles are, which people are involved in executing activities, etc. So this is just the tip of the iceberg. Here you see some screenshots in PROM using this data set. So here I'm showing a process model where I have these 2 sliders that I mentioned before in the context of commercial systems. So we are looking at all activities because this slider is up, and we are looking at, let's say, the most frequent paths. Only if this slider is completely up, we are looking at all the paths. So we see all activities and just the most frequent paths. I can zoom in, I can zoom out, I can interact with this process model in all kinds of ways. If we have a normative process model, so you have a process model not describing what has happened, but what you would like to happen. It's possible to edit models. Then you can see deviations from this normative model, which is indicated in blue. The deviations are indicated in red. So what you see here is, for example, that the log compared to the process model, we skipped 37 times sending the invoice, and we skipped the payment 1600 times. And this is of course the case because I left out of the model the possibility to cancel. So this is probably not the best normative model that you would like to look at, but it shows the idea. I can simply select any of these deviations, and I can drill down, and then I see the individual orders in which these deviations take place, and they are highlighted in red. And so here we see an event that happened in reality, but that was not allowed by the model at this stage. It may also be that that if we compare log and model, we see that events are missing. Things should have happened according to the model, but did not happen. So this is the conformance view. We also, of course, have a performance view because the log contains information about when events take place. So if we have start events and complete events, we can see the duration of activities with certain probability distributions. We can also always see waiting times, even if we just have a complete or a start. So we can visualize such information, and activities become more red if the delays are bigger in front of that activity. We can also animate the event log, and then we have these colored tokens, and we can influence the color of the token. So the color of the token can be based, for example, about the value of the corresponding order, or the type of customer, or whatever feature we are interested in. So we have this seamless abstraction where we have sliders and we can interact with the data in all kinds of ways. What is important, that's why I'm showing this slide, is that if you are doing process mining, there is not such a thing as the best model, the only model that we have there. It depends on what you would like to do. The same as if you are, let's say, learning decision trees, you also make certain, let's say, design decisions, set parameters in a particular way to get the decision tree that you are interested in. So next I'm going to show you a demo in PROM. In the course you will use PM4Py. I'm showing you this in PROM because that's easier and more interactive in such a way that you have an idea how these tools work. I just started PROM, and if I do so, then this is the starting screen that we see first. Given this starting screen, I can, let's say, load different objects. For example, event logs. I cannot just load event logs. I can also load all kinds of artifacts, like models and stuff like that. We can also load logs in different formats. I just load an XCS file, which is in the IEEE standard format for event data, but I can also load CSV files or other types of files containing event data. In this pool, we see all the artifacts that we have loaded into PROM, and in favorites, we only see the important ones. I can visualize this, and if I do that, then we see that this event log has 1266 cases and over 8,000 events, and there are 8 different activities. If we look at the frequency of activities, then we can show all kinds of overviews showing the relative frequencies, what it starts with, etc., etc. This is very unsurprising. We can also look, and that's more interesting, we can explore the different trace variants. So that's the view that I'm showing you here. So what you see here, there are 9 trace variants, and each variant has a certain frequency. So the top one is happening 503 times. So these are all the orders that had the following sequence of activities: place order, send invoice, pay, prepare delivery, make delivery, confirm payment. We can inspect each of these 503 cases that follow the same variant, and for every event we can see by which person it was executed at what time, what quantity, and all kinds of other attributes. As I mentioned, at the top we see the most frequent ones. If we go more to the bottom, we see, let's say, traces which have a lower frequency. So these are the rare variants in the process. So for example, if we look at the bottom one, there are only 2 orders that follow this pattern. And this pattern is rare because people pay before they get an invoice. So I can drill down in these 2 cases, and then we can see again lots of details about that specific instance of the process. So here we can explore the raw data. We can also, that is often very insightful, we can also generate a so-called dotted chart. And let me first reorganize this a bit. So I sort this on the start time of the case, and I color this based on the event name. What we now see is that we see, let's say, 1 dot for each event. If I zoom in, you can see that that is actually the case. So every dot corresponds to an event, and we can inspect these events. On the x-axis, we see the absolute time. So we see the time at which the event takes place. And on the y-axis, we see the different trace variants. So if we follow one horizontal line, we see all the events that correspond to that particular case. So if we do that, in a way, we are again looking at it in the same way as we were doing here, but now visualized based on time. So again, I should restore my view just as I did before. And so I can interact with that, and what you can clearly see is you can see daily patterns, you can see weekly patterns. You can also see that all the cases start with a blue dot, and if we look in the legend, then we see that the blue dot corresponds to placing an order. So we can take this visualization. We can also take, and we can zoom out, and we can select things, export subsets of data, etc. We can also change the color of the attribute. So for example, I can change the color of the attribute based on the product. And now if you look at the legend, you can see that it has changed. Now the different events have a color based on the product that they refer to. Since we are focusing on control flow, let's just take this view. What I now do is I'm going to change the x-axis, and I'm going to change the x-axis into the time since the case started. So now the picture looks like a mess, but I'm going to sort now the case based on the duration. And now you see a very nice pattern. So again, every row corresponds to a particular case. They are now sorted based on duration. So at the top one, you see the case that takes the cases that take the least amount of time. At the bottom, you see the cases that take the most amount of time. They all start at time 0 because it's relative time. We can again see we always start with, as I can zoom into this part, it always starts with placing an order. And then in most cases, not always, you can see that it is followed by sending an invoice. Then if people do not pay, we start sending the reminders, etc. So we can interact with such data, we can select data, etc., etc. However, this is basically data visualization with a temporal component. What is very different is that based on this we can start to create process models. So a process model, there are like many different minors. If I do this, let me start by simply creating a so-called directly follows graph, a concept that we will come back later in this course. So what we now see is that, let me move the slider up. So now every node corresponds to an activity. We see the frequency of the activity. We also see arcs, and the arcs indicate how often a particular activity was followed by another activity for the same case. In this example, for the same order. So this is showing all the activities and all the paths. The yellow, let's say, tokens correspond to cases that are flowing through this model. And we have the ability to let's say, reduce the number of activities. That is, we can move that down and it gets simpler and simpler. This way we again see all the activities. We can also lower the paths. So that means that we abstract from certain, let's say, infrequent paths. And the more I go down, you more see the more frequent path. So now you may wonder, okay, now I squeezed the model in this most frequent variant, but reality was very different, as we could see when we were looking at this model. So if I move this down, I can choose another view and I can show the deviations. And now we see, with respect to the blue process model, we can see the different deviations. In the next lecture, we will focus on conformance checking, and we will go back looking at such, let's say, kind of properties. If I move it up again, we again see all the behavior, and I could also show you the sojourn time. So that's basically the times in between different activities, because we only have complete here. And the more red the activities are, the more time is spent in front of this activity. So now we get an indication of where the bottlenecks are. So we see that for confirmed payment, the time in front of this activity is typically only 23 hours. In some of the other ones, you can see that it is multiple days. So for cancel order, it is almost 2 days. So this is the directly follows graph, and what you constantly see is that we are animating the flow based on this. This is a purely sequential model, so we do not see concurrency. So for example, if we think about some of the activities here, they are not happening in a fixed order. So more interesting are, let's say, discovery techniques, that if I go back to the initial pool, I basically remove this one and I call another minor, and I now call the visual inductive minor, which looks very similar, but internally it is completely different. You now see a similar model as we had seen before, but I would like to draw your attention on, for example, this construct. So what we see here is that make delivery and confirm payment are two activities that are not happening in a fixed order. And this minor is able to detect that they are typically executed, but not in a fixed order. So we can play with this model. Again, we can change the set of activities that we look at. So I can lower it, make it more frequent. This way we again see all the activities. I can also play with the path. So if I move it up a bit, then we start seeing, let's say, more of the behaviors. So if I look at, for example, send reminder, we can see that of these cases, there are 646 for which no reminder was being sent. Then there are the 620 for which reminders are being sent, but often multiple are sent because we go back 360 times. Here we can skip the payment. We skip that 149 times, and again we see the same parallel block at the end. So again, we could also show the sojourn times. just as I showed before, but I just want to show that you can also show that for these parallel constructs. It's also possible to show deviations. So for example, if I move the paths a bit down, and now I show the paths and the deviations, we now see from the deviations with respect to the blue model. So the next lecture we will talk about conformance checking, and this will become, let's say, more clear. If I go back to the model that I just had, so suppose that we are happy with this model. There are many more things that we can do. We can change the color of the tokens. We can generate all kinds of statistics. What we can also do is we can take such a model and we can convert it to other types of models. So we can take this model, we can say export model, accepting PatriNet, and we have now generated a PatriNet based on this inductively mined model. Later in the lecture I will explain more about PatriNet, and I will also show you how this particular algorithm works. What is important to see now is that PROM and other process mining tools provide many different discovery techniques to discover these models. So if you are familiar with PatriNet, you will see that this is indeed a model that I showed to you before. So the inductive miner goes first from first learns a process tree using inductive mining, and then you can map it onto a PatriNet and do all kinds of additional analysis. What you can also do is you can call the so-called heuristic miner, and that is also one of, let's say, over 1500 plugins in the PROM framework. Here you can choose different visualization, so you can also show the directly follows graph. It's very similar to what I showed before. So if I lower it, I see more paths. If I move it more up, I see less paths. So I can again visualize paths and leave out paths that are infrequent. We can show a so-called causal net or heuristic net. What we now see, for example, if we zoom into the part with prepare delivery, this is showing that after prepare delivery we start both make delivery and confirm payment, and we can only finish if we have chosen this branch when both of them have been completed. We can take such a model and we can of course also generate the corresponding PatriNet, and this is the PatriNet that basically shows the behavior that I was before showing in terms of a causal net. So hopefully this gives you an impression of the many things that you can do with the PROM tool. What is now important for the remainder of the lecture is that we first look at discovery. So that is the process of starting from event data and automatically learning process models that are describing the data. Okay, I hope that this gives a good idea in how these tools work. For example, PROM, but you will also see that commercial tools are able to do, let's say, many things that are very similar. Okay, let's take a look at a more realistic scenario. The data that I showed so far was highly synthetic and simplified. Here I'm looking at a typical case that any organization has, that is the so-called purchase to pay process. So if organizations are using SAP, this is handled by SAP, but there are, let's say, many other systems that organizations use to handle this. So this is, let's say, the buy side of an organization. So an organization needs to purchase products, also this university, but that holds for any organization. And when you buy products, there is typically a certain process in doing this. And here you see the activities that need to be executed in such a process. So in this simplified model, there are, let's say, 4 sequential activities. Then we have receive goods and receive invoice, which can happen in any order. So you should read this as a partial order. And after receiving the goods and after receiving the invoice, we pay the invoice. So this is the PowerPoint version of the purchase to pay process. And this is what, if you ask people what is the purchase to pay process, what are the activities, they will draw something like this. So this is what people say that the process is, but this is what it really looks like. So it is very normal that if you have like a larger organization that has thousands of such purchase cases, then, so for example, in this example, if you have processes that have like 700,000 different cases, it is quite normal that you have, let's say, 7,000 unique variants. So the models looks very much like spaghetti and very different from the model that you see here. This is just to illustrate the value of automatically generating these models and being able to interact with these models, to zoom in, to zoom out, to look at the frequent deviations, to look at the costly deviations, to see how you can improve such processes. So if you look at these, so on the previous slide I said, okay, there are 7,000 different variants. Let's take a look at one of these deviations, and one of these deviations is the price change. This is an example of a frequent deviation that is happening in 8% of the cases in this example. And if there are such price changes, one or more, on average this adds a delay of 4.5 days. So we see this deviation and we can drill down what are now, for example, the suppliers that are causing such price changes. Having this information may help you to kind of to improve the process, to avoid, let's say, adding delays and adding this extra work. Another example, so something that in this data set is happening in 2% of the cases, are let's say the situations where we never receive the goods. So the goods are paid without ever being received. This is happening in 2% of the cases, and this may indicate fraud. We can drill down on these deviations and we can see what they have in common, and we can take countermeasures to address these. So these were, let's say, two of many different variants. Here you see two more deviations. I could show many more, but they show the basic idea that these deviations from the happy path are super interesting for organizations. And it's a different type of data science than the things that we have been talking about before, because it takes into account this process perspective. So process mining can be used to uncover performance problems, so we can see where there are unnecessary or unexpected delays, and we can automatically generate root causes for these delays by combining these process discovery techniques together with, let's say, many of the techniques that we have seen in previous lectures. This is something that I will come back to in much more detail in the next lecture. So we can address performance problems and we can address compliance problems. So things that, I don't know, should have happened but did not happen, or the other way around. This may also indicate things like, for example, conflicts of interest. So there are two activities that are not supposed to be executed by the same person in order to have the so-called 4I principle. If this 4I principle is, let's say, violated, then process mining can also be used to do that. But that requires that you extend these models also with resource information. So possibilities are endless to do these types of things. To say a bit about the practical perspective, because before we go into, let's say, concrete algorithms, many organizations in Germany, in general in Europe, but also at the global scale, are using process mining. It's fair to say that, let's say, the north of Europe, so Germany, the Netherlands, are leading in this field, and I think Siemens is a prime example. So Lars Reinkemeyer, who is leading the process mining activities within Siemens, like last year he gave a guest lecture here in Aachen, And then he was telling about, let's say, the spectacular use of process mining within Siemens, where there are over 6,000 active users of process mining. They're using the Sloanus system. They're saving millions and millions of euros by avoiding these types of friction that I hinted at before. And this is done at an amazing scale. So for example, if you look at the order to cash process, so before we looked at the purchase to pay process, that was the buy side of an organization. Now we look at the order to cash process, that is the sell side of an organization, where Siemens has 30 million cases, over 300 million events, and very surprising, for this basic process one can find 900,000 different trace variants, which shows that process mining really has value in such applications. There are many other applications, I will not dwell on that. I just showed this picture to just indicate to you that this is not just based on SAP or administrative processes. This also applies to production processes, machines that are in the field. It applies to, let's say, logistic systems, but for instance also how people use social media, how people use certain products in their home. So for example, like a nice example is that BMW is using process mining to see how people are using the navigation system in the car. These are just examples of how you can apply process mining. What is interesting to know, also if you want to, let's say, specialize later in this field, you have to realize that, let's say, at the end of the 90s, I was basically the only person working on this topic together with my research group. For a very long time, nobody in the world was doing this. Then several of my students started companies, let's say around 10 to 15 years ago. So for example, a company like Fluxicon that is selling the disco tool that I showed earlier was founded. In 2011, a bit later, the Sloanus company was founded by 3 students that started with the PROM process mining software and then built their own based on these ideas. So commercial tools have been around for, let's say, over 10 years, and only what we can see in the last couple of years is that there is this spectacular adoption in industry, like for example the things that I showed of Siemens. So this shows a bit the development of the field, and I hope that this illustrates is that it's very interesting for you, given the expertise, given that the expertise is present here in Aachen, to, let's say, specialize later in this field that is so rapidly growing in importance also in industry. If we look at tooling, then the things that I showed you so far was the PROM tool set. What you will see in the instructions and what you will use in the assignment is PM4Py, which is Python based. There are many other, let's say, open source platforms that you can use. So there are, for example, things based on RapidMiner or K9. There are also, let's say, libraries based on R. So there is something to choose from. On my slides, I will basically just show, let's say, the PROM tool, because that shows things in a very direct and visual manner. There are over 35 process mining tools available today. Here you can, let's say, see some of the names. Like some of these companies are small, others of these companies are very big. Like for example, Sloanus and UiPath or Abbey. These are examples of large organizations, but there are also many, let's say, smaller ones. If you look at the Disco tool set, I already showed that to you before. This is the way that it looks. It's an example of a tool that is super easy to use, but it's typically the the product that is used in a project. It's not used, let's say, in a continuous way. If you look at tools like, for example, Celonis and also UiPath, which is integrating Process Gold, which is not a spin-off of, let's say, my old university. If you look at these tools, they do not aim at the data scientist, but they aim at, let's say, bringing these process mining results to, let's say, a large number of users in the company. And so if we go to Siemens, these are thousands of people. If we go to BMW, there are also over 1,000 people using these types of systems, lowering the threshold to use process mining. Celonis, I think, is a very, let's say, spectacular example. I think by many dimensions, it is the most successful German young IT company that exists. Some people say this is the new SAP, which they are now valued 2.5 billion, which is not so bad for a startup that started in 2011. This is just to make already some advertisements for things that I will also say at the end. That there are many, let's say, thesis projects, many interesting jobs in this space. Okay, so this was the overview. Let's now get back to the basics. In the previous lecture, I already showed you what event data are. We have also seen that before. So every row corresponds to an event, something that has happened. We require at least the case ID, activity name, and timestamp, as we have seen before, also in the initial example in this lecture. There may be all kinds of other data that we can use, for example, to generate predictions, or to use decision trees to understand choices, stuff like that. But in the basics that we will focus on today, we need to have a case ID, activity name, and timestamp. This is about student data. This is about order data, like you will find in SAP or Salesforce or something like that. Again, what is in green is mandatory. All the other stuff can be used, but is not mandatory in the first step. We can also look at healthcare data, as I've mentioned. Again, we see this pattern. We have a case ID, corresponds to a patient. We have the activity, that may be things like an X-ray, a CT scan, doing a particular type of surgery. And we have the time at which this has happened. There may be other information, like, for example, the doctor that worked on a particular patient. This is also what we have seen before. I'm just trying to refresh things that we looked at in the context of sequence mining. So a process consists of cases, a case consists of events, and events may have all kinds of attributes. Here we simplify things, and although an attribute, an event may have different attributes, we basically just focus on the activity name, and within a case we are only interested in the ordering. So we abstract from time, resources, and all kinds of other information. And so this is basically showing the mapping. So the event log shows the process as a whole. Then every case corresponds to a sequence of activity, and an event corresponds to an activity in one of these sequences. Technically, a log is a multi-set of sequences of activities after stripping away and abstracting from all kinds of other attributes. So this is the basic input. So now we have a very simple problem. We reduce the event data to just a multi-set of sequences of activities, and we are using that as input for discovery. So in the next lecture we will look at other things like conformance checking, building predictive models, enhancing models with bottleneck information, but today we just look at discovery. And discovery is a scientifically super challenging question for a variety of reasons. So we have the real process that nobody really can touch, nobody really can see. this real process leaves event data. Note that we only see example executions. We do not see all the things that are possible. We just see the things that have happened. And based on these event data, which are example sequences, we need to learn a process model. That's what we look at. I already indicated that this is very difficult and tricky. We only see what has happened, so we only see examples. We do not see any negative examples. We do not see what could not happen, and so we cannot just see this as a classification problem. We would like to distinguish between, like if we talk about cases fitting into the model, they may be fitting completely. They may be very different, or they may also be almost fitting, as we say then. If we look at a process model that has a loop, we have infinitely many traces. And because we have infinitely many traces possible in the model, we can never expect them to happen in reality. And so here, sometimes I talk about Murphy's law for process mining, that basically says anything is possible if you wait long enough. So in the end, the process model should not describe what is everything that could happen if we would wait for centuries. That is not an interesting question. We are typically interested in, let's say, the model that is, for example, describing 80 or 90% of the behavior. So we are now going to reduce the problem, as I just indicated, where we look at the simplest way to look at process discovery, where our input is just this multi-set of activity sequences called traces that I introduced before. And from such, let's say, very basic data, we would like to automatically learn process models. For example, such a process model expressed in terms of a Petri net here. And I hope that these examples intrigue you a bit, like how that can be done. I will basically describe two approaches. The first approach is a bottom-up approach, using very much, let's say, a Petri net view on the world. I will also explain a completely different approach, which is top-down, which is using more, let's say, a view that we would also have if we would be doing programming, where we are using operators like sequence, choice, etc., to compose a process model. What I mean exactly by that will be clear soon. So I assume that all of you have some basic understanding of Petri nets. If not, please use the pointers that I gave before. Then you will see that it is very easy to understand, let's say, the rules of the game when we look at the Petri net. Here, just to refresh your knowledge a bit, we are looking at accepting Petri nets. So these are Petri nets with an initial marking indicated by the black dot here. And we have a final marking. And if we reach the final marking, note that marking stands for state. And the state is described by a configuration of tokens over different places. The final marking that we look at, the final state, our target state when we are done, is when there is a token in place end. So what kind of executions do we have? So the first trace would be as follows. So in the initial state only A can happen. So we execute A. A is producing 2 tokens. And what we now see is that B is enabled, C is enabled, and E is enabled. So we now execute any of these activities. What we just did is we executed B. So we consume this token here and we produce the token here. Because E's input places are now not all marked, so P1 is empty, E can no longer happen, B of course can also not happen because this token is gone. The only thing that can happen is C, because D is also not enabled because it requires a token here. I can now execute C because that's the only possibility. And in this state, none of these activities A, B, E, C is enabled. The only one that is enabled is D, and we have reached the final marking. So A, B, C, D is an example of a trace. So I'm now playing out the model. Of course, process discovery is doing the reverse. You see examples and you would like to automatically construct something like that. But we first look at the problem in the forward direction. And then later we focus on discovery. Now we look at the second scenario, the second possible trace according to this model. So again, we start with activity A, because in the initial marking that is the only activity enabled. Then we are again in this situation where both B, C or E can happen. Assume in this scenario that C has happened, then the only thing that is possible is D. It's very similar to the initial trace. At the end we can only do D after we have executed B and C, and then we reach the end. A third possible execution of this model is that again we start with A, but now instead of starting with B or C, we start with E. E requires both tokens on place P1 and P2. Both of them are consumed. They are produced for the output places, and in one step we consume 2 tokens and we produce 2 tokens, and we can immediately go to D, and after D we have reached again the final marking. So these are the 3 possible behaviors of such a model. Here I'm showing you a model that looks very similar, but you should note that in the middle the arcs have been reversed. So first E had P1 and P2 as input places, now E has P3 and P4 as input places. So this means that after executing B and C, we can execute E to go back. So we have a trace like in the beginning, A, B, C, D, that is still possible, but we also have a trace like this. So A, C, B, then there is a token in P3 and P4. Then we can execute E. After executing E, there is again a token in P1 and P2. Then we can, for example, execute B, C, and finally D. So now there are, because of this loop involving E, we can always go back again to the state before executing B and C. So there are infinitely many possible traces showing that if we look at process discovery, we can never expect that the log contains all the possible executions of a model like this. So if we look at it in a bottom-up perspective, and you understand battery nets now, then the definition of the enabling of a transition is that a transition is enabled if each of the input places contains at least 1 token. If a transition contains no input places, that means that it is continuously enabled. My initial marking is the empty marking, my final marking is also the empty marking. There are no places, so we cannot have any other markings actually. And this model allows for any behavior involving any combination of the 5 activities that you see here. So we can have E, C, E, A, A. So this is any behavior, and whenever we add a place, then we are adding a constraint. So if we are adding this place A, so a connection between A and E as input and B as output, then we are constraining this because the number of times that B has happened is lower or equal to the number of times that A and E has happened. So it cannot be that B happens before A happens or before E happens. At the end, because we want to have the final marking, at the end, the number of times that A and E is executed should be exactly the same as the number of times that B has been executed. So places are like constraints that restrict the behavior. And here I'm showing simply some examples. So if we add a start and an end like this, then we have the requirement that A should happen precisely once and D should happen precisely once to reach the final marking. So in general, you can think of this problem as discovering places. And if you take a course in process mining, then you will find different algorithms to be able to discover such places. So there are many possible approaches. So there are things based on heuristics, like the alpha algorithm and heuristics miner. There are all kinds of approaches that provide formal guarantees, that they prove that under certain circumstances they create a model which is identical to the model from a behavioral point of view that you started with. You can also use genetic and evolutionary approaches, where you basically randomly change, combine models with an evaluation function. So just like, let's say, gradient descent, you try to improve the quality of the model over different generations. There are various approaches that you can use to support such a bottom-up approach. This shows a screenshot where we are applying the heuristic miner to SAP data, and here you can see, let's say, the Petri net which was learned from such data. What you see here is there are all kinds of sliders to, again, controlling whether we would like to have a model that explains all the behavior or just the dominant behavior. So that was the bottom-up approach, starting from a Petri net that allows for everything and then adding different places. The next step, we use a top-down approach. So what we now do is we start very different. We are actually using a technique called inductive mining. And inductive mining actually refers to a family of approaches that is using this top-down approach that I will describe next. So again, the input is identical. We also would like to create a process model, but rather than starting from Petri nets, we start from something that is visualized here as process trees. So you can think of these as hierarchical process models. So I'm just going to sketch the approach. So we load as input a bunch of traces. So every trace that you see here corresponds to a case. Note that this is technically a multi-set of sequences of activity names. That's what we defined before. But I'm using this, let's say, visually more appealing approach. There is some redundancy, so we see that certain traces are happening for multiple cases. So A, B, C, D, we will see that there are 3 cases having this pattern. So this is our input, just as before with the bottom-up approach. And our goal is to learn hierarchical models that are using operators that most of them you're very familiar with. So sequential composition, you can imagine, okay, we have a process which is followed by another process. We have exclusive choice, so we have a choice from several sub-processes and we pick one. There is parallel composition, again we have different sub-processes, but we do not choose and pick one to be executed. We basically execute all of them in any order. So they can be interleaved in any way possible. There is the redo loop, which is a combination of a repeat until and a while do construct. I'll explain that in a minute. We have normal activities that are atomic steps, and there is something called a silent activity. So the silent activity means that we are skipping certain activities. And this is very common in the field of, let's say, process models, that you need to add such silent activities to, for example, model behaviors which are not directly coupled to an activity which has a visible behavior. So, for example, if I'm skipping an activity, I will not see the message, I'm now skipping this activity. You will simply see nothing that is represented by this tau activity. So if we map this onto Petri net, so a silent activity can be seen as executing a transition which does not leave any traces in the event log. There is a normal activity, just represented by a Petri net transition. This is sequential composition. What is important to realize is that A, B, C, etc. could all be sub-processes. So here, like A, B, and C correspond to, let's say, atomic activities, but they in themselves can again be complete processes with hundreds of different activities. So we have sequential composition that are executed in sequence. We have exclusive choice. We pick one of them, and again here I have the remark, here I show atomic activities, but this could be the choice between several sub-processes. Parallel composition, I think, is also still easy to understand. So we start here, and after the start there is this silent activity that is starting up all of these different sub-processes that can be executed in any order, and only when all of them are done we can end. So this is you can think of this as an AND split, and you can think of this as an AND join, which is synchronizing, let's say, the different parallel branches that we have started. The redo loop is a combination, like it's a generalization of while, do, and repeat until. So this construct has the following semantics in terms of a Petri net. So we start, and there is a token here. Then we can do A and stop. So it allows for the execution of just A and then ending. Or it allows for that we execute A and then we do not stop. We go back via B. So we do A, B. And after B we again need to do A. And then we can stop, or we can go through this loop multiple times. So this can have the behavior A, B, A, B, A, B, A, end. That's a possible behavior. And again, note that A and B can be complete sub-processes. So I'm sure this relates very much to your programming experience to see what these things mean. So now the goal is, if we have raw data, we are trying to learn automatically such process models using operators such as sequence, choice, parallelism, loop, etc. The first step is that, given an event log, we create the so-called directly follows graph. These are the graphs that, if you look at commercial tools, this is what they initially present as an end product. But here we just use it to detect certain patterns to create higher level models. So if you look carefully, then you can see that all of these 13 cases starts with A and ends with D. So this directly follows graph is showing that from the outside we always start with A. There are 13 cases and always end with D. Then we can look at the other arc. So for example, this directly follows graph says that A is directly followed by B 6 times. So if we look in the log, then in this first variant, which happens 3 times, we see A followed by B. So that's already 3 times. Then we have 2 times A followed by B, because this variant is happening twice. And finally we have this unique variant. So we have 3 plus 2 plus 1 is equal to the 6 that we see here. And I could do the same for all the other arcs, it's simply counting. So this is incredibly scalable. We can use things like MapReduce and all kinds of other things. This is always possible. Then, based on the directly follows graph, we do a we try to look for a so-called sequence cut. I will simply show it and then explain. So a sequence cut is a partitioning in the graph in such a way that the arcs are always going in one direction. So here we go from this let's say model, this subset of activities, to this one, and we go from this one to that one, but we never go in the opposite direction. So we basically partition the activities in such a way that the way that they are connected are always connections, let's say, only in one direction and not in the other one. If that is the case, we say there is a sequence cut, and if we have such a cut, then we can basically color the activities based on in which part of the, let's say, directly follows graph they are. And so here we have three, let's say, subsets. The red one consisting of just A, the green one consisting of B, C, E, F, and the blue one consisting of B. So we have identified the sequence cut, we color the activities in these three different colors, and then we can color basically the event logs based on this. And then we split our event data in a red log, a green log, and a blue log. And in the sequence example, this is completely trivial. And so all of our 13 cases is starting with an A. So if we look at this log focusing on just A, like all the different instances just have an A. The same at the end with the D, so that's what we can end here. And in the middle we have this, this green part that is remaining. And because we have a sequence cut, the behavior is that we first execute this process, then this process, followed by this process. Note that this example is very simple and misleading. Of course, this the red part normally is like a collection of activities, and also the blue part is a collection of activities, making it more interesting. So the red sublog and the blue sublog are already so-called base cases, because they just talk about one activity. So they can be trivially converted into, let's say, normal atomic activities. Then the green part remains, but in principle, right, it could be that in each of the subtrees we still have a complicated log. Then for each of these sublogs we basically repeat the same principle. So this was my green log. Then we again create a directly follows graph. For the sublog it looked like this. And again we look for certain patterns. So now we can look for a sequence cut, but that is impossible. We are unable to partition this graph that meets the requirements of such a sequence cut. So what we do next is that we look for other cuts. So we look for a parallel cut, we look for a choice cut. This is not possible, but what is possible is that we find the so-called, let's say, a cut corresponding to the loop. So it looks like this. Here I'm visually showing it. Let's say the exact details of this cut are, you don't need to know that exactly. They are described in the book in a very precise manner. But if I state it to you, let's say informally, is that if we have this do part and this redo part, then we should always start and end in the do part, so in the top part. The bottom part may not be connected to, let's say, to the environment. So it may not be, we may not start with F or E, and we may not end with F or E. So that is one requirement, that starts and ends are just in the do part, so the top part. Moreover, the inputs of the redo part should be exactly the same as the outputs of the do part. So where the do part is ending should be exactly these points where the redo part is starting. Similarly, if we look at where the redo part is ending, that should correspond to the activities where, let's say, the do part could also start coming from the environment. So this should be the same as this, and this should be the same as this. As I said in the book, this is described in a precise manner. So it meets these requirements. We can again color it. Now we have just a binary partitioning, so we just need two colors, red and green. Here I'm coloring the activities. I can again color the activities in the log. So we have now the red activities, the red sublog and the green sublog. Because we are now using a loop cut, we cannot simply concatenate, for example, this BC with this BC. Basically, each time that we leave the red part, we are starting a new case if we are projecting this on the red part. So you should kind of think of this as that you take these sequences of events here and you add them here to the bottom. Note that they, like later if we talk about concurrency, this does not need at all to happen in a sequential way, but based on this construct, each time we have left, let's say, the do part, we basically start a new case. So here we have 13 cases, and if we do this, then we see that we have more cases. We have in total 20 cases. I just put all of these things underneath each other, and then we see 11 times BC, 9 times CB. We see this green, let's say, subsequences. We also see this one we put at the bottom. So we have 2 plus 2 plus 1 plus 2 times 1 is in total 7. That explains the number here. So again, we create, let's say, sublogs, and then we can repeat the whole principle. So this is again an event log. This is an event log. We can again construct directly follows graphs. Here we can identify a sequence cut. Here we can find the so-called parallel cut. That basically means that that any activity here is followed by any activity here, and vice versa. These are ways of again identifying a sequence and identifying a parallel construct. So this is what we end up with. We did not see the choice construct here, but the choice construct we get if the directly follows graph has unconnected parts. Then all the unconnected, the different, let's say, connected components, they correspond to exclusive choices. So this is the final model. This is again a visualization of the process that I just showed. So we start with a log, and then we build a directly follows graph that leads to a partitioning of the different events in the log, and in each step we kind of reduce the number of activities per sublog until we reach the situation where sublogs just have refer to a single activity. Then we have a base case and we can simply add activity. And so this is the model that we just learned. Such models can be represented in all kinds of ways. Before we saw already results using inductive mining. They were visualized like this because this is easier to understand than this tree structure. But in fact it's exactly the same way, it's just a different visual representation. Earlier I showed you that these process tree operators can be mapped onto Petri nets. We can also remove, let's say, transitions that we do not really need, and then we get, let's say, clean Petri nets like this. We can also represent it in terms of BPMN models, in terms of UML activity diagrams, in terms of UML state charts, and whatever notation you like. Because of the hierarchical structure, it's very easy to generate all of these different languages. So the inductive mining algorithm is interesting, although I just scratched the surface. You only saw, let's say, the basic idea. The basic algorithm has certain guarantees, and so the models are always sound. The models are always able to generate the event log that was used as input. If you make the assumption that the event log was generated from a process tree having certain properties, then it's guaranteed that the process tree with exactly the same behavior is generated. So there are formal guarantees that you're able to reproduce behavior. That's typically not what you want in reality. You need to deal with infrequent behavior. Event logs may be extremely incomplete. So there are all kinds of extensions to deal with these more real-world behaviors. There are also variants which are super scalable, which only learn directly follows graph once. Compare this to the FP growth algorithm. You just do a single pass through the data, and based on that you can construct these process models. You can also distribute this. You can make streaming variants of this algorithm, etc. So at the end, some more, let's say, context on tooling, and also some pointers to work that we are doing in the group. I will not do that for other topics, but because process mining is one of the key topics done within our PADS group, I spent some time on this. PROM is the de facto standard in the scientific world, served as examples as an example for many commercial vendors. PROM supports in total over 1,500 plugins. That makes the tool also very, let's say, difficult to use for people that are new to the topic. These commercial tools are much easier to use. So the goal that we always had was to convince commercial vendors like Celonis, Fluxicon, UiPath, QPR, and I could mention, let's say, 35 other vendors. We try to convince them to embed these IDs in their commercial tools. That has been quite successful, as I mentioned before. If you look at the tools that we as a group support, so PROM is this de facto standard for many years. Interestingly, what you now see is a diversification of open source software based on the different platforms that exist. So in our group, we, for example, also have, let's say, process mining suites based on general tools like RapidMiner and K9. If you search online, you will find them very easily. So if you have these platforms, you can easily install process mining capabilities on top of that. What is relevant for you in this course, and also where a lot of the group's development efforts go into, is PM4Py, which is a Python-based variant of PROM. Because in this course we don't want to use like many different platforms and many different systems. That is why we are using PM4Py in this course. In some of the other courses you will see things like PROM and RapidMiner. If you're interested in diving deeper into the topic of process mining, I would recommend taking the course Business Process Intelligence. This is like a basic, let's say, core process mining course, that is highly recommended. If you would like to specialize and go deeper into this area, I would also recommend the course Advanced Process Mining, which goes much more into the details of the algorithms, for example, proving certain properties of the inductive mining algorithm that I just sketched, or proving properties of certain decomposition techniques. We also offer various practica and seminars, and there are the standard ways of getting information on this. We of course also have many thesis projects in this area. I will tell a bit more about that at the end. Because we are now more or less in the middle of the course, I would like to make you aware of this, that there are these possibilities. So while making your assignments, while learning for the exam, it may be things that you can think about, whether you find this interesting. If so, please visit our website, where we always offer such projects. We are also very well connected with industry. So if you do a master project in this space, it will also be very easy to find a job in industry later, because industry is screaming for, let's say, process mining experts. If you would like to dive much deeper, we also always have PSD positions. We also have HEVI positions. With the HEVI positions, yeah, you can go to our website and find information about this. Please do not apply for a HEVI job if you did not take one of the process mining courses yet. Or if you have completed this course successfully with a good grade, then you can apply, but don't start applying without having any knowledge about process mining and proven that you can do these types. But if you're good at this, there are always opportunities to offer such positions. To come to a conclusion, so this was the first lecture of 2 on process mining. So today we focused on the unsupervised approach, which basically boils down to process discovery. So we just have event data, we know nothing, and we would like automatically try to learn models that show us what is going on, where are bottlenecks, stuff like that. It starts from event data, and the goal is to learn end-to-end models. The goal is not to learn patterns. And now this table that I showed to you when we were in the lecture on sequence mining should be much clearer. The a priori algorithm and similar algorithms like that are typically looking at patterns, local patterns. Process mining aims to learn, let's say, these more end-to-end processes, showing bottlenecks, showing deviations, etc., etc. The focus is on models that show activities, but next to activities, we can also visualize resources, we can visualize decision points in terms of decision trees, etc., etc. Compared to sequence mining, we also look at higher level behaviors. And for example, when I showed you the inductive mining technique, you could see that discovering these loop operators, discovering these parallel constructs, these things are at a much higher level of abstraction than the things that we have seen before. I should also add that sequence mining is focused on item set data. Process mining is much more general. It can basically apply to any domain where one could draw in a meaningful way a process model about a specific type of cases. More on this, let's say, in the next lecture. So the next lecture will be also devoted to process mining. We will then cover things like, for example, conformance checking, where we take as input an event log and a process model, and we kind of calculate where the deviations are and how severe they are, and how we can generate, let's say, machine learning problems on top of combining logs and models. More about this in the next lecture. After that, so we have now been focusing very much on data with a temporal component. In the 2 lectures that come after that, we focus on textual data, which is of course also data of a very specific time. And just like we had to focus on processes, we also have 2 lectures devoted to text mining. See you next time.